All right, so let's go over the homework. So the question I intended to grade was question 4. And it was an inductive proof, and it asked you to show the following. It said, prove sum from k equals 0 to n of 2 to the k equals 2 to the n plus 1 minus 1. In other words, 1 plus 2 plus 4 will be 8 minus 1. If you add up powers of 2, you get the next power minus 1. And we kind of know this from doing computer stuff, from doing 250, things like that. If you write a binary number with all ones, it's 1 less than the next power of 2. That's really what this is saying. So you wanted to prove this using mathematical induction. So I've said this every time that we've done an inductive proof, I think, you want to start by stating a proposition. And almost nobody did that. So I'm going to do this the same way we've been doing this, but think about why we're doing each of these things. We cannot talk about what P of 1 says until we know what P of n says, or P of x, or P of something, right? P of n is a family of propositions. And we're going to talk about P of 1 and show that that's true. And then we're going to assume P of n is true, and then we're going to try to prove P of n plus 1 is true. But before we can do any of that, we've got to know what P of n is. So let P of n be the proposition which says the sum from k equals 0 to n of 2 to the k equals 2 to the n plus 1 minus 1. And I don't mind if you write this with a dot, dot, dot. If you say something like the proposition 1 plus 2 squared plus up to 2 to the n equals 2 to the n plus 1 minus 1. This is more formal, but we all know what you mean by this, right? But I clearly have to see something like a statement, what is P of n? And now you can say P of 1 says, and now you can write the thing that most people wrote, which is sum from k equals 0 to 1 of 2 to the k equals 2 to the 0 plus 2 to the 1 equals 1 plus 2 equals 3. And this equals 2 to the 1 plus 1 minus 1, which is also equal to 3. And this is your demonstration that P of 1 is true. So after you've written something like this out, you can say, therefore, P of 1 is true. But you got to have something equivalent to all of this before you get to proving your base case. Right? Does it make sense? You've got to state what P of n is. You can't just jump in and say P of 1 says this, because we don't know what P is. And you can't just write this and say our base case is true. You've got to name your base case, right? We're proving something about a family of propositions. The base case is proving it for one particular element of that family, usually P of 1, P of 0, something like that. Okay, here's what I don't want to see. Don't write. So don't write P of n equals the sum from k equals 0 to n of 2k equals 2 to the n plus 1 minus 1. Because there's math here, and when we write A equals B equals C, that also tells us A equals B, and it also tells us A equals C, and it tells us B equals C. And as soon as you write this, what you are saying is P of n equals the sum from k equals 0 to n of 2 to the k. And this is not a proposition. It's not a declarative statement. I know what you mean. You mean to say that P of n equals this proposition, right? But we don't use equal signs for statements, okay? We're going to avoid that. If you want P of n to represent this statement, say something like, let P of n be this proposition.
Would it be correct, like, to put a colon instead of an equal sign?
You can do a colon, but don't. I run into this problem with KVL, KCL. I use a colon, and over time, the colon gets wider and wider, and eventually it becomes an equal sign, usually on the exams. Okay, so take the extra wordage right? Have fun with it. Do calligraphy or something, I don't know. Yeah?
If you really, like, if you were in a hurry, could you just say let p of n be?
The prop will work.
Okay.
7 letters. That'll work. But yeah, because this can be an equation, it can be a statement, it can be a theorem, it can be an assignment statement if we're programming, right? In our case, we mean it to be a proposition. But that's usually not what we mean in our lives when we say A equals B. So yeah, spend the words, at least say the prop. All right, now we've proven the base case. We can move on to do the inductive step. So it's worth, when you're demonstrating a proof on a homework especially, but even on a test, to say something like, let's prove P of n implies P of n plus 1. Guide the reader in understanding what it is that you've written. What's about to follow is a proof that P of n implies P of n plus 1. So we can state P of n, that's the hypothesis or the assumption or whatever you want to call it. If we're doing this, I would say that's the hypothesis. So P of n is true. And P of n is a statement that the sum from k equals 0 to n of 2 to the k equals 2 to the n plus 1 minus 1. That's the definition of P of n. And almost nobody seemed to do a 2-column proof where they had a statement and a reason for it, right? And I can follow the reasoning usually, but your goal is to demonstrate this clearly, right? Not to me, but to somebody who may not have seen this proof before. And so each statement that you write, you want to explain why this statement is true, right? This is true because it's the hypothesis. This is true because that's what P of n is defined to be. All right, so at this point, some people made a bad move. So don't do this. We have no business writing that. Okay, this is what P of n plus 1 says. It's what we're trying to show. As soon as you legitimately write this in your proof, you're done. You've proven this if-then statement. Now you just say, therefore, P of n for all n. But unless this follows directly from this, you can't write it. Okay, you can put it in that ignore section. I saw some ignore sections. That was great. But don't write this down. What a lot of people did was they wrote this, and then they did some arithmetic, and they eventually showed 2 to the n plus 2 minus 1 equals 2 to the n plus 2 minus 1. And then they said, therefore, P of n plus 1 is true. And you cannot go in this direction. What you've shown is that if P of n plus 1 is true, then this statement is true. So you've shown P of n plus 1 implies 2 to the n plus 2 minus 1 equals 2 to the n plus 2 minus 1. But that does not prove P of n plus 1. Right? So this is the whole thing with converses and inverses versus contrapositives, right? This may very well imply that. If I win the lottery, I will come to work on Friday because I love my job, right? I show up to work Friday, hey, you must have won the lottery. No, it doesn't work that way, okay? So if you do this, you're trying to say that this implies that. And it's just, logic doesn't work that way. So that's why we always have to write down something that's true. And if eventually we write down some things and we end up with P of n plus 1, then we can say this is true. All right, so don't do this thing. I used up all my paper there. So what do we got? We've got the definition of P of n. So most people added something to both sides, right? A few people multiplied both sides by 2. That also works. But let's add something to both sides. So sum from k equals 0 to n of 2 to the k plus, and let's add one more thing, 2 to the n plus 1. And I'll put some parentheses here just to be clear, will absolutely have to equal what the sum of 2k is, 2 to the n plus 1 minus 1, also plus 2 to the n plus 1. That's algebra. If a equals b, a plus x equals b plus x. So we add the same thing to both sides, and we still have an equality. And now you've bridged that gap from where we are to where we want to be. Now we just have to fill in the details. So we can rewrite this as the sum from k equals 0 to n plus 1 of 2 to the k. That's just using the summation. And we can write this as 2 to the n plus 1 plus 2 to the n plus 1 minus 1. And now this is 2 times 2 to the n plus 1 minus 1. And 2 to the n plus 1 times 1 more 2 gives you 2 to the n plus 2 minus 1. And all we've done is write equivalent forms to the right side. So this is still true. And now you have to say this is p of n plus 1, right? Therefore, p of n plus 1. And that's the definition of p of n plus 1. And if you go from something like this and say, therefore, p of n plus 1, you're missing some steps, right? Certainly, if you go from here and then say, therefore, p of n plus 1, you're missing a few steps. Right? Your goal is to lead the reader through. Well, we can take this and we can turn this into 2 times 2 to the n plus 1. We can turn that into 2 to the n plus 2. And we can write this as the sum. And now this is the exact form of what p of n says. Right? P of n says the sum from 0 to n of 2 to the k equals 2n plus 1, where n is just a placeholder. So if we use n plus 1, this should be 2 to the n plus 1 plus 1, 2 to the n plus 2. So now you've got p of n. The last thing you want to say is, therefore, p of n for all n bigger than or equal to 1. And that's the punchline. That's what you're after. It's what you want to show. Your conclusion is not simply, therefore, p of n. Right? We started off by assuming p of n. Your conclusion is that because p of n implies p of n plus 1, p of n is true for all n bigger than or equal to whatever our base case was. So you really want all these steps in there, right? State what the proposition is. Make sure it's clear it's a declarative statement. And then write out what the base case says. Demonstrate the base case is true, and then state p of 1 is true, or whatever base case you had. And then assume p of n, argue logically from things that follow starting with p of n until you get down to a clear statement that shows p of n plus 1 is true. And then say p of n for all n. The reason for that is mathematical induction. And that gives you a perfect inductive proof. So does that make sense? So on Canvas, there's some practice induction problems that you can work on. There's also more problems in the textbook. And the odd problems all have solutions in the back of the text. So if you want to practice these, right, there's plenty of things you can work on. And if you want to come by and show me your proofs for something and say, is this right, I'm happy to look at those and go through details with you. Because I really want people to be able to do an inductive proof by the time they're done with this course. It's a really good reason to understand propositional logic. Proving that the product of two even numbers is even is fun. But induction is something that we actually use. And it ties into computer science nicely, so it's good to be able to do that. And there'll definitely be inductive proofs on the midterm and on the final. So that's another good reason to be able to do them. All right, so let's run through the questions. As soon as I can find the right section. Which section of the book is the induction? 3.5? Is it 3.7? Okay. I don't have a table of contents on my PDF reader. All right, so we talked about this one a little. So prove that that is equal to n plus 1 factorial minus 1. Let P of n be the proposition. And you know what? I'll let you do this too. How's that? So I don't have to rewrite it. So that's the proposition P of n. Plug in an n, we get a value. So P of 1 says 1 times 1 factorial equals 1 plus 1 factorial minus 1. 1 plus 1 factorial is 1, and 2 factorial minus 1 is 1. So P of 1 is true. So suppose P of n, so 1 times 1 factorial plus 2 times 2 factorial up to n times n factorial equals n plus 1 factorial minus n. That's just a statement of what P of n is. And we want to get to where we're adding all of this plus n plus 1 times n plus 1 factorial. So let's add that to both sides. And that's going to be equal to whatever the right-hand side was plus the same thing. So all we've done is add this term on both sides. Right, and again, if I had written that this was n plus 2 factorial minus 1, I'm done. My proof is fallen apart at that point. But you can add the same thing to both sides. And so we said the other day, let's try factoring out the n plus 1 factorial. So n plus 1 factorial times 1 plus n plus 1. So that gives us this term, it gives us this term, and then we still have a minus 1. And this is n plus 1 factorial, and n plus 1 is n plus 2, and we have our minus 1. And if you multiply all the integers up to n plus 1, and then you multiply by n plus 2, that's just n plus 2 factorial. And we still have a minus 1. And the left side hasn't changed. And this is P of n plus 1. Bless you. So assuming P of n, we proved P of n plus 1. And therefore, P of n itself is true for all n bigger than or equal to 1. And the reason is mathematical induction. All right, 4 we already talked about. 6 was the generalized De Morgan's law. We did the other version of De Morgan's law. So any questions on the version from the book where you were complementing the ands instead of complementing the ors? So let's look at 8. So let P of n be the proposition a to the n minus 3 to the n is a multiple of 5. And in the book, I don't like the way they phrase that. They said, let P of n be a to the n minus 3 to the n is a multiple of 5. I don't think that's totally clear. If you put that statement in quotes, like let it be, quote, a to the n minus 3 to the n, that's a little clear. But I would say let it be the statement or the proposition that a to the n minus 3 to the n is a multiple of 5. And so our problem is to prove P of n for all n bigger than or equal to, did they want 1 or 0? Natural numbers, I don't know. Let's do bigger than or equal to. Let's do 0. So we can write what P of 0 says. So it says a to the 0 minus 3 to the 0 is a multiple of 5. A to the 0 minus 3 to the 0 equals 0. And that is a multiple of 5. It's 5 times 0. So P of 0 is true. So assume P of n well, we want to show that a to the n plus 1 minus 3 to the n plus 1 is a multiple of 5. So a to the n minus 3 to the n equals 5 times some constant, some integer. Okay, that's what it means to be a multiple. We want to do something to get an a to the n plus 1 and a 3 to the n plus 1 in here. And we can't do that with just a single trick. We can't just multiply by itself or something, or multiply by 8 minus 3, because numbers don't work that way. So let's do our ignore section. And we want to show a to the n plus 1 minus 3 to the n plus 1 equals 5 times some constant. Well, if we multiply both sides by 8, right, a to the n becomes a to the n plus 1, 3 to the n becomes 8 times 3 to the n, and 5k becomes 5 times 8k. And I'm being a little deliberate in how I'm arranging these things. So this is still a multiple of 5. Right, this is a to the n plus 1. We'd really like 3 to the n plus 1. And this is just a trick, and we talked about this a little bit the other day. So the idea is 3 to the n times 8 can be written as 5 times 3 to the n plus 3 times 3 to the n. Right, so we can break that 8 into a 3 plus 5 and reverse distribute. So 5 3 to the n plus 3 to the n is 8 3 to the n. But this is now 3 to the n plus 1, and this is a multiple of 5, which is why we think this might be helpful. So 8 to the n plus 1 minus, and instead of 8 3 to the n, we're going to do 5 times 3 to the n plus 3 times 3 to the n equals 5 times 8k. And now you can kind of see good things are going to happen. So this is going to be minus 5 times 3 to the n, and this is going to be minus 3 to the n plus 1 equals 5 times 8k. And just bring this term on the other side. 8 to the n plus 1 minus 3 to the n plus 1 equals 5 times 8k plus 3 to the n. And this is a multiple of 5. Because it's 5 times this integer. K is an int, n's an int. So assuming P of n, we've shown 8 to the n plus 1 minus 3 to the n plus 1 is a multiple of 5. That's what P of n plus 1 says. So P of n plus 1 is true. Therefore, P of n is true for all n bigger than or equal to 0 by mathematical induction. So people found the tricks, right? In most cases, they knew how to bridge that gap from P of n to P of n plus 1. But the other part of this is the formalism, right? And I really want you to think about the formalism and practice doing something along these lines. All right, make sense? All right, do you want to hear about muddy foreheads? This is another inductive thing, and it's Friday, so it's a good thing to talk about. So I'll let you think about this over the weekend, and if you want, we can talk about it Monday. It's induction, but it's a sneaky form of induction. So here's the setup. There's a teacher with a classroom full of students, and the students go out for recess, and they play outside. And they come in for class, and the teacher looks very upset and says, there are students in here who have mud on their forehead because they were playing in the mud. Okay, you're not allowed to look at a mirror. You're not allowed to touch your forehead. You can't use your smartphone. You're not allowed to ask somebody, do I have mud on my forehead? Okay, so no self-inspection directly or indirectly. So the teacher says there's people in this classroom who have mud on their forehead, and said, everybody who knows that you have mud on your forehead, raise your hand. And nobody raises their hand because nobody's sure if they have mud on their forehead or not. And the teacher says again, everybody who knows that you have mud on your own forehead, raise your hand. And nobody raises their hand. And the teacher says it again, anybody who knows that you have mud on your own forehead, raise your hand. And keeps saying this, and all of a sudden, after some number of times, every kid who has mud on their forehead raises their hand. So that's the whole setup. And you can prove that that will happen after asking the question n times. If there are n kids with mud on their forehead, after n iterations of asking the exact same question, all n kids will be able to raise their hand and nobody else will. And it's an inductive thing. So you can think about that over the weekend in between physics and stacks and queues and whatever else. All right, so we're going back to number theory. So we were talking about modular arithmetic. And we had left with this kind of cool property which said if A is congruent to B, mod M, and C is congruent to D, also mod M, then A plus C is congruent to B plus D, mod M. This should have a cool name, but it doesn't. It's just a theorem. So congruence is always talked about relative to some modulo, right? So for example, 17 is congruent to 3 mod 14, right? Which says that if you divide this by 14, you get the same remainder as if you divide this by 14. It also says the difference of these two is a multiple of 14. And 141 is congruent to 15 modulo 14, because this is one more than a multiple of 14. This is one more than a multiple of 14. So this theorem is saying that if we add these together, 158 will be congruent to 18 modulo 14. So we have hope of defining some kind of addition within a system of modular equivalences. Well, here's why this theorem is cool. So if we work strictly modulo m, so I don't want to keep writing mod m, mod m, mod m, but anytime we do anything, we always take a number and we reduce it modulo m. So we get some number between 0 and m minus 1. So here's the corollary. A plus b, I am going to write mod m, is going to be the same thing as whatever a is modulo m plus whatever b is modulo m. Where, again, we take that whole thing, and if it's bigger than or equal to m, we reduce it modulo m. So what does this mean? It means we can define a new type of addition. We can call it plus with a little m for a subscript. It's called modular addition, or addition modulo m. And when we add two things with this funny plus sign, we take the result and we reduce it modulo m. And the consequence of this theorem is that we can take two numbers, add them together, and reduce it modulo m. Or we can take those two numbers and first reduce each of them modulo m, and then add them together. And we'll get the same result. And that follows out of this theorem. So it makes this operation well-defined in some sense. If we have two numbers, 17 and 3 are both equivalent, we can add 17 to something, we can add 3 to something. We should end up with the same answer in the final reckoning when we reduce everything modulo 14 in this case. And it turns out there's also a multiplication operation. A times b mod m will be equal to a reduced mod m times b reduced mod m. And this is the powerhouse of modular arithmetic. And you already know this in some cases. For example, multiplying those numbers would take us a while, right? But suppose we want to know if we multiply these numbers and we express the answer modulo 10, what are we going to end up with? We're going to end up with 6. Why? 3 times 2 is 6, right? But why does that work? Because if we take this and we reduce it modulo 10, this is just congruent to 2. And if we take the second number and reduce it modulo 10, it's just congruent to 3. And so our theorem says this times this modulo 10 will be the same thing as 2 times 3 modulo 10. And we know that already. When we multiply numbers, we can find that rightmost digit by just multiplying the two rightmost digits. But this is why it works, right? Because this is the same as multiplying what each of these is congruent to, which is just the rightmost digit. So here's two other long, horrifying numbers. And I ask you, if I multiply these, will the result be divisible by 5? And the answer is clearly yes, right? Why is the answer yes? Because the bottom one's divisible by 5. But in terms of our theorem, this is congruent to something, modulo 5. But since this is divisible by 5, this is congruent to 0. Modulo 5. So when we multiply these, we've got to get something that's congruent to 0 times something, which is just 0, modulo 5. So we've already recognized some of these things and taken advantage of them through our lives. But we're really doing modular arithmetic. And when we recognize that, we can start branching out from here and do lots of things that aren't necessarily as obvious. All right, so let's do some other examples, and then we'll go back to some applications of this. So let's work modulo 12. So everything from here on down is going to be modulo 12. So 7 times 2 is going to be congruent to what? I mean, it's certainly congruent to 14, right? But what else is it congruent to? 2. Because 14 is 2 more than a multiple of 12. If you take 14 divided by 12, you get 1 with 2 left over. That 2 tells you what it's congruent to. All right, if we do 3 times 3, that's congruent to 9. It's also congruent to other things, right? It's also technically congruent to minus 3. It's 3 less than a multiple of 12. But usually we want something between 0 and 11 if we're working mod 12. All right, if I take 13 and I add 14, what do I expect that to be congruent to using our theorem? 3. Why?
Because 13 is 1 more than 12, and 14 is 2 more.
Mm-hmm. Yep, that's congruent to 1, that's congruent to 2. We expect their sum to be 3. If I multiply these, I expect that to be congruent to 1 times 2, which is 2. If you actually multiply those out, you should get a number that's 2 more than a multiple of 12. But this is a whole lot easier to do, right? All right, here's a weird one. What is 3 times 4 congruent to? 12, which is also congruent to 0. And this is our first hint of something different. Because we have 2 numbers that are not 0, and we multiply them, and we get something that is 0. That's a little weird. Okay, that doesn't happen with regular numbers. But when we're working congruent sum m's, this will happen. And this can do good things, and it can also cause you problems. And in particular, it's going to make it tricky to define division. Because if we define division based on this, we could say 0 divided by 3 is equal to 4. And that's a little bit weirder too, right? Divide 0 by something and get something weird. So let's just look at that. So let's look at modulo 4, and let's make a table. And let's do multiplication. All right, so here's the nice thing about working over modulo something. Every possible integer that we can think of is congruent to either 0, 1, 2, or 3, mod 4, right? 5,416,000 is going to be congruent to 0 mod 4. Positive, negative, doesn't matter. It's always going to be congruent to one of these 4 numbers. So we can define a multiplication table for numbers mod 4. And all we got to do is take our 2 numbers, see what each of those is congruent to, and we can look up what the product is. So, well, anything times 0 is going to be 0. Anything times 1 is just going to be whatever the anything was. 0 times 2 is 0. 1 times 2 is 2. What about 2 times 2? 0. What about 3 times 2? 2. All right, 3 times 0 is 0. 3 times 1? 3 times 1, it's Friday. 3. 3 times 2, 6, which is 2. And 3 times 3? 1. Yeah, 9, which is 1 more than 8. So there's a multiplication table, mod 4. And we certainly expect this column and this row, because when we multiply by 0, we should get 0. But this is a little unusual. If we do a multiplication table for integers, we get zeros here and here, but nowhere else. All right, let's do mod 5. All right, I'll do the first row and the first column for you. And I'll do the second row and column for you. All right, 2 times 2? 2 times 3? You said 1. 2 times 4? Yeah, 8, which is 3. 3 times 2, we already said was 1. 3 times 3? All right, 3 times 4. All right, 12, which is 2. 4 times 2 is 8. We did 2 times 4, so that's 3. 4 times 3. All right, 12, which is 2. And 4 times 4, 16, which is 1. This is true, which is pretty interesting. So why does it do that?
It's almost like a binary subtraction.
Yeah, so what is 4 congruent to mod 5 besides 4? -1. So when we multiply by 4, we're actually multiplying by -1, which means we're taking the negative of things. And this 4 is actually -1. This is actually -2. This is actually -3. And this is actually -4. So that's exactly what it's doing. It's counting down.
So, yeah, I don't think it was this way, or no, it's not this way on the keyboard, but this particular one, if you ignore the rows of zeros, it's kind of like step where like every row and every column
Yes.
those 4 numbers,
Mm-hmm.
as well as every, no, not every square, but every one column.
So every row and column contains 1, 2, 3, 4. That's a cool observation. And in fact, it's because of that that we could define division mod 5, right? We know that if we want to pick any number from 1 to 4 and divide by any number from 1 to 4, we get some other number. We can say 4 divided by 3 gives us 3.
That only works because none of those others are multiples of 5.
It works because none of those others are multiple of 5. In fact, what that means is there's no zeros in this purple region. So when there's no zeros in here, we have a special case of something that will eventually be called a field. We don't talk about field theory in here, but it makes this modular system a field, whereas this is not a field. So why did a 4 give us zeros over here and a 5 did not? What's the difference between 5 and 4 that's critical here? 5 is prime. So if we work modulo any prime number, we will get the same appearance. No zeros, and every row and every column will contain every number from 1 up to that prime minus 1. And if we work modulo something that's not prime, we will have zeros in here. So prime numbers are starting to creep in to relevance here.
So if you have a program, they could check these tables,
Mm-hmm.
you could possibly have a
You could use that to check prime numbers, yes. May not be quicker though. But if you had a quick way of doing that, yes, absolutely. All right, so that's a good stopping point. So Monday we will start talking more about primes, and then we'll get into some really good stuff.